Welcome to session 3 with focus on Markowitz portfolio optimization. The learning goals for session 3.3 are: you should be able to base your security selection on the efficient frontier of risky assets. You know the different capital allocation steps as well as the separation property. And students should also understand the power of diversification. Markowitz portfolio optimization model. As we have learned from the previous session, portfolio construction consists of 3 steps. First, we identify the risk-return combinations available from the set of risky assets. Second, we identify the optimal portfolio of risky assets by finding the portfolio weights that result in the steepest capital allocation line. Third, we choose an appropriate complete portfolio by mixing the risk-free asset with the optimal risky portfolio. The first step, security selection, is to determine the risk-return opportunities available to investors. These are summarized by the minimum variance frontier of risky assets as shown on the next slide. The minimum variance frontier is a graph of the lowest possible variance that can be attained for a given portfolio expected return. Notice that all the individual assets lie to the right inside the frontier, at least when we allow short sales in the construction of risky portfolios. The part of the frontier that lies above the global minimum variance portfolio therefore is called the efficient frontier of risky assets. For any portfolio on the lower portion of the minimum variance frontier, there is a portfolio with the same standard deviation and a greater expected return positioned directly above it. Hence, the bottom part of the minimum variance frontier is inefficient and can be cancelled. Markowitz portfolio optimization model. The second part of the optimization plan involves the risk-free asset. As before, we search for the capital allocation line with the highest Sharpe ratio. The capital allocation line generated by the optimal portfolio P is the one tangent to the efficient frontier. This capital allocation line dominates all alternative feasible lines. A portfolio manager will offer the same risky portfolio P to all clients regardless of their degree of risk aversion. Individual investors choose the appropriate mix between the optimal risky portfolio and T-bills. The client's risk aversion comes into play only in capital allocation, the selection of the desired point along the capital allocation. Capital allocation and the separation property. The first task, the determination of the optimal risky portfolio. This is purely technical. Given the manager's input list, the best risky portfolio is the same for all clients, regardless of risk aversion. However, the second task, capital allocation, depends on personal preferences. Here, the client is the decision maker. In practice, different managers will estimate different input lists, and therefore deriving different efficient frontiers and offer different optimal portfolios to their clients. More risk-averse investors put less in P, less risk-averse investors put more in P. The power of diversification. As introduced in the previous session, the concept of diversification is limited to systematic risk. Given the tools we have developed, we can reconsider this intuition and at the same time sharpen our insight regarding the power of diversification. Recall the general formula for the variance of a portfolio composed of n risky assets. This is also called a naive diversification strategy, in which an equally weighted portfolio is constructed. We have the following formula for variance and covariance. Continuing from the previous slide, we can rewrite the portfolio variance as shown here. Now examine the effect of diversification. When the average covariance among security returns is zero, as it would be if all risks were firm-specific, portfolio variance can be driven to zero. We see this from the equation. The second term on the right-hand side will be zero in this scenario, while the first term approaches zero as n becomes larger. Hence, when security returns are uncorrelated, the power of diversification to reduce portfolio risk is unlimited. The irreducible risk of a diversified portfolio depends on the covariance of the returns of the component securities, which in turn is a function of the importance of systematic factors in the economy. Risk reduction of equally weighted portfolios. To see the fundamental relationship between systematic risk and security correlation, suppose for simplicity that all securities have a common standard deviation and all security pairs have a common correlation. Then, the covariance between any pair of securities is the correlation times the variance. Our previous formula becomes, by replacing the covariance with the correlation times the variance, the following equation. In the table, as one would expect, standard deviation gets smaller as we include ever greater numbers of securities in the portfolio. We have two cases for correlation 0 and correlation 0.4. As one would expect, portfolio risk is greater when correlation is equal to 0.4 versus correlation of 0. More surprisingly is that portfolio risk diminishes far less rapidly as n increases in the positive correlation case. The correlation among security returns limits the power of diversification. Optimal portfolio and normal returns. The portfolio optimization techniques we have used so far assume normal distribution of returns and standard deviation to be fully adequate measures of risk. However, potential non-normality of returns requires us to pay attention as well to risk measures, to focus on the worst case losses such as value at risk or expected shortfall. Unfortunately, the impact of diversification on tail risk cannot easily be estimated. A practical way to estimate value at risk and estimated shortfall in the presence of fat tails is called bootstrapping. Risk pooling and the insurance principle. Risk pooling means adding uncorrelated risky projects to the investor's portfolio. Applied to the insurance business, risk pooling entails selling many uncorrelated insurance policies. This application of risk pooling as a mean to reduce risk has therefore come to be known as the insurance principle. Risk sharing. Risk sharing can be achieved by spreading risk across many investors so that each investor bears only a fraction of total risk. Risk pooling, together with risk sharing, results in portfolios with a superior risk return trade-off. For example, a portfolio with the same expected return but lower volatility. By enabling investors to combine risk sharing with risk pooling, capital markets allow firms to engage in risky projects without imposing undue risk on their shareholders, and in this way facilitate the collective economy's ability to undertake large possible risky ventures. Investments for the long run. Now turn to the implications of risk pooling and risk sharing for long-term investing. Think of extending the investment horizon for another period. Analog to adding another risky asset to our portfolio or adding a new insurance policy to a pool of existing ones. We should know that risk does not fade in the long run. An investor who contemplates investing in an attractive portfolio and considers investing in a given amount in that portfolio for one period would find it preferable to put money at risk in that portfolio in as many periods as it is feasible. However, to limit cumulative risk, he must also correspondingly decrease the risky budget in each period. If time diversification really were a way to limit risk, one would expect it to allow longer-term investors to increase the amount invested in the risky portfolio without increasing the risk of final wealth, but that is unfortunately not the case. We are at the end of session 3.3. After having carefully studied the slides and relevant chapters in the book, please start with the review questions.